Okay, thank you everyone for coming and thank you, Jacob. So today I'm going to be talking about this question: do first-class constraints generate gauge transformations? And as I'm going to motivate later, answering this question has several consequences that are not only important for understanding the physics better, but also bear on several topics in the philosophy of physics as well. And in this talk, I'm going to present what I call a geometric perspective on this question. In particular, I'm going to use a standard geometric framework in what I think is a novel way to resolve a debate between the affirmative and negative answer to this question. And as a spoiler, I will argue that it resolves it in favor of the affirmative answer. But first, in order to get a better grip on this question, we first need to know what a first-class constraint is and what a gauge transformation is. So starting with the latter, what is a gauge transformation? Well, there are several definitions in the literature, but the guiding notion that's going to be important for the purposes of this talk is that a gauge transformation is a transformation that connects physically equivalent descriptions of the same state or the same history of a physical system. And in this way, what a gauge transformation is intrinsically connected to the interpretation of a theory in that it requires a notion of physical equivalence. Moreover, I've used the term state or history in this definition, since as we will see later on, which term that one uses in this definition is part of the contention in the literature. But one thing that's generally agreed upon is that the existence of gauge transformations indicates that there is arbitrariness in the solutions to the equations of motion. The reason being that if we have physically equivalent states or histories within our theory, then our equations of motion will be such that there is not a unique evolution from some initial point. And this leads to apparent indeterminism in the theory, apparent because it's regarded as a feature of our mathematical description and not of the world. So the second thing we need to know is, what is a first-class constraint? Well, we need some more machinery in order to answer this, and I'm going to describe this in detail later. But broadly, what a constraint is it's a function that imposes restrictions on what it counts as a physically allowed state. And the first-class constraints are those that commute with each other in a particular way. But in order to make these things more precise, we need what's known as the constrained Hamiltonian formalism. And this is a formalism that originates particularly with these figures, Paul Dirac and Peter Bergman. And their motivation for this formalism was to provide a framework that links constraints of certain types to gauge freedom. And in doing so, would allow one to determine what the gauge invariant variables are, the variables that do not vary under the gauge transformations, which are otherwise known as the observables, as a way, firstly, to restore determinism in one's theory by defining the theory just in terms of these observables. And very importantly for these figures, particularly as a step towards quantization. And indeed, a standard way of quantizing a theory known as canonical quantization comes from this formalism. So the constrained Hamiltonian formalism is of interest in the philosophy of physics for several reasons, but the most notable reason is that the constrained Hamiltonian formalism is the basis of this puzzle in the foundations of physics known as the problem of time, which is that when general relativity is put in this framework, or indeed any time reparameterization invariant theory, one finds that the observables are unchanging with time. And in as much as one thinks of the observables as the physically meaningful quantities, this suggests that the physically meaningful quantities do not change with time. And so we don't seem to have a meaningful notion of change in our theory. And this bears particularly on the metaphysics of time. So just to mention two particular topics that have been discussed in the philosophy literature in relation to the problem of time. The first is the debate about the correct philosophical view about change that originates with McTaggart and the distinction between the A series and the B series views of change, which has been brought up in the philosophy literature in relation to the problem of time, particularly by Irvine with the paper titled Thoroughly Modern McTaggart, and then a response by Maudlin, Thoroughly Muddled McTaggart, where Irvine argues that the problem of time suggests a new account of change that he dubs the D series. And second, the problem of time has been discussed in relation to the substantivalist versus relationalist debate about the ontology of space and time. And here I just point to two papers by Karim Thébault, the first of which discusses which of these views is suitable in light of the problem of time in the non-relativistic case, and then the second paper with Sean Gribb considering the relativistic case. But the focus of my talk is going to be on the notion of a gauge transformation that particularly comes from Dirac. And this is the view that each first-class constraint generates a gauge transformation. And Dirac thought that this definition had several important consequences. The consequence that's going to be the focus of this talk is that he thought that on the basis of this, one should extend the Hamiltonian in order to include all of the gauge freedom. Whereby extending the Hamiltonian, what this means is adding some additional terms to the form of the Hamiltonian, such that the Hamiltonian is really an equivalence class of Hamiltonians, and the difference being some arbitrary factor in the form of the Hamiltonian. So just to motivate a bit why one might want to make this move, if we think back to the definition of a gauge transformation that I gave earlier, the presence of gauge transformations in a theory indicates that there is arbitrariness in the sense that there are multiple mathematically distinct evolutions that are possible from some initial state. But if we don't include any of this arbitrariness in the Hamiltonian, then it seems that our dynamical equations only have one possible solution from some initial point. And this effectively hides the arbitrariness that is present. So it seems that if we want our dynamics to contain this arbitrariness, we ought to add it into our description of the Hamiltonian. So the Dirac view of gauge transformations has arguably become the standard one, and is the one that's presented in several textbooks on the foundations of the constraint Hamiltonian formalism. But there have been several arguments that in fact the Dirac view is not right. So just to give a few of the problems that have been presented for the Dirac view. First, there have been some counterexamples to the claim that first-class constraints of a particular kind, called the secondary ones, and we'll describe what those are later, generate gauge transformations. Second, there have been counterexamples to the claim that not only the secondary first-class constraints, but that each first-class constraint generates a gauge transformation. And finally, there have been arguments that Dirac's proof of the gauge transformations is faulty and limited in scope in various ways. And in light of some of these problems, some people have proposed what I'm going to call the alternative view of gauge transformations, which is that rather than it being that each first-class constraint generates a gauge transformation, rather it's a specific combination of them that generates a gauge transformation. And this view concludes that unlike Dirac, who thought that one ought to extend the Hamiltonian, this alternative view concludes that one need not extend the Hamiltonian, at least to the extent that Dirac did. Sometimes it might seem like people also take the stronger view that one should not extend the Hamiltonian in this way. What's important for our purposes is just that this view denies that Dirac was right about the definition of a gauge transformation, and then concludes that he was also wrong to think that one has to introduce this extension to the Hamiltonian. So in this talk, I'm going to try and provide a resolution to this debate between the Dirac view and this alternative view of gauge transformations. In particular, what I'm going to argue is that by using a geometric formulation of the constraint Hamiltonian formalism, one can see that the reasoning in both the Dirac and the alternative view of gauge transformations is flawed, but that in this formalism, the correct reasoning validates the definition of a gauge transformation given by Dirac, namely that each first-class constraint generates a gauge transformation. And in doing so, I will diagnose the reasons that one might be led to this alternative view. So before I get into my argument, I'm first going to consider some reasons that one should care about this question. So the first reason, as I suggested before, is that the constraint Hamiltonian formalism is the basis of this puzzle, the problem of time. And in particular, the formulation of the problem of time that is most relevant for what I'm going to be talking about is that when the Hamiltonian, the thing that generates the dynamics, is itself one of the first-class constraints, the Dirac view of gauge transformations leads to the conclusion that time evolution is just the unfolding of a gauge transformation. And on the understanding of a gauge transformation as connecting physically equivalent states, this suggests that all the states along some evolution are just physically equivalent, and so one doesn't seem to have a meaningful notion of change. But if the Dirac view doesn't hold, as proponents of this alternative view suggest, then perhaps this is a way to avoid the problem of time. The second reason to care about this question is that the problem of time really falls under a wider issue of how we should interpret those variables that vary under the gauge transformations. On the one hand, it seems that there are reasons to think that we should just interpret them as physically meaningless because they are the things that vary under these transformations that we think connect physically equivalent states or histories, and therefore that we should just remove them from our theory by what's known as quotienting out by the gauge transformations. But on the other hand, there have been some suggestions that, in fact, these gauge variables can have a kind of interpretational significance, and therefore that we shouldn't remove them from our theory because they play an ineliminable role. And so getting a better understanding of what the gauge symmetries are, and in relation to this, what notion of physical equivalence is at play, might help to shed light on this question. And a third reason to care about this debate is that determining what the gauge symmetries are in the Hamiltonian framework, and in comparison, what the gauge symmetries are in the Lagrangian picture, is important for determining in what sense and whether these two pictures can be said to be equivalent, because the gauge symmetries are going to be a guide to how much structure these two pictures have. And some advocates of the alternative view of gauge transformations argue that it's only their view that matches the Lagrangian gauge transformations, whereas the Dirac view does not. And in fact, that this is a reason to adopt this view because we should assume to start off with that these two pictures are equivalent. Okay, so the rest of my talk is going to go as follows. First, I'm going to describe Dirac's recipe for constructing a constrained Hamiltonian theory and look at the arguments that Dirac gives for the Dirac gauge transformations. Then I'm going to look at two particular arguments that have been given against Dirac and in favor of this alternative view. So the first is an argument by Brian Pitts that one can find counterexamples to the Dirac view. And in particular, I'll look at one particular counterexample that he gives. And second, I'm going to look at the argument that Dirac's proof is limited that's given by Pons. Then I'm going to turn to this standard geometric formulation of the constraint Hamiltonian formalism and use it in what I'm going to argue is a novel way to resolve this debate between the Dirac view and the alternative view. And then I'm going to consider, finally, some possible responses to my argument and some unresolved issues. Okay, so starting with Dirac's recipe for constructing constrained Hamiltonian theory, the idea is that first one starts with a Lagrangian that's written in terms of some position variables and some velocity variables. And here we're going to assume throughout that we have an independent time parameter. This Hamiltonian framework can be extended to the case where we don't assume this, but right here we're just going to assume we have this independent time parameter. Then what we do is we define what's known as the canonical momenta variables as the derivative of the Lagrangian with respect to the velocities. And on the basis of this definition, one finds in some cases, the cases that are of interest to us, that we have some constraints on the relationship between the position variables, the QIs, and the canonical momenta variables. And here I write these constraints as phi being a function of these two things being equal to 0, and the constraints are indexed by m here. And we call these the primary constraints because they arise from this move from the Lagrangian picture to the Hamiltonian picture. Next, we define what's known as the total Hamiltonian, which one might recognize as just being equal to the usual Hamiltonian, the sum of the momenta times the velocities minus the Lagrangian. But now we also have an additional term, which is an arbitrary combination of the primary constraints, where the u here is just an arbitrary function of the canonical variables and time. And we're taking here a sum, which is here denoted by the fact we have this lower and upper index. And the idea of this total Hamiltonian is that when the constraints hold, that is when this relationship between the Q's and the P's is equal to 0, this total Hamiltonian is just equivalent to the usual Hamiltonian. And from this, we can derive the equations of motion in this theory for some function f as just being the derivative of that function with respect to time is equal to the Poisson bracket of that function with the total Hamiltonian. And next, one uses the fact that it ought to be the case that the primary constraints continue to hold over time. And what this means is that if we plug the primary constraints into the equations of motion, it should be that it equals 0. And by doing this, we find in some cases that there are in fact further constraints on the relationship between the Q's and the P's that we call the secondary constraints, since they arise from thinking about the primary constraints under the equations of motion. And then we can repeat this process by putting these secondary constraints into the equations of motion, setting them also equal to 0. And we might find some further constraints that are sometimes called the tertiary, etc. constraints, but we're just going to call them all the secondary constraints. And finally, we can classify our constraints according to whether the Poisson bracket with a constraint with all the other constraints is 0 when the constraints hold, in which case we call that constraint first class. And if it's not equal to 0, then we call it second class. And one thing I don't have in this picture is that the second class constraints, in fact, allow one to fix some of the arbitrariness in the total Hamiltonian. And so one can refine the dynamics at the end of this process by writing the total Hamiltonian just in terms of a first class Hamiltonian and an arbitrary combination of the primary first class constraints. But importantly, as long as some of the constraints are first class, we are going to still be left with arbitrariness in our total Hamiltonian. So just to give an example of this recipe in action, we're going to consider the case of electromagnetism without any sources. So we start with a Lagrangian, which here we're going to write in terms of a vector field A and a potential V. And one might recognize this as just being the integral of a half E squared minus a half B squared, where E is the electric field and B is the magnetic field. But it turns out to be convenient in moving to the Hamiltonian framework to write the Lagrangian in terms of this vector field and a potential. So now with the Lagrangian, we can define the canonical momenta conjugate to the vector field A and the potential V. And what we find when we define the canonical momenta is that the canonical momentum conjugate to V is just equal to 0. And so this gives us our one and only primary constraint, that P0 is equal to 0.
Clara, I'm so sorry to bother. There was a question in the chat, just a brief technical question from Enrique. On the previous slide, were you using the equalities there to denote weak equality that is up to constraints?
Yeah, I was using them as a weak equality. Thank you, Enrique. Yeah, they should really be kind of the curly equals, where we're saying they're equal to 0 when the constraints hold, or yeah, the weak equality notion. Thank you.
Great, thanks. Please go on ahead.
Thanks. Okay, so just as Enrique pointed out, really we should think of this primary constraint as being a weak equality here. Okay, so we have this one primary constraint, and then we can define the total Hamiltonian, where the important thing here is that the last term in this expression is the primary constraint with an arbitrary function multiplying it here given by a u. And then we can derive the equations of motion, which here I just write for this vector field A and the potential V. And then importantly, when we put our primary constraint into this equation of motion and set it equal to 0, we find that we in fact have a secondary constraint given by the gradient of the momenta conjugate to A. Again, we should really think of this as a weak equality. And this is our one and only secondary constraint. And finally, the Poisson bracket between these two constraints is equal to 0 when the constraints hold. And so both of these constraints are first class. Okay. So now we're going to turn to how Dirac understands the gauge transformations. So Dirac defines a gauge transformation as something that relates any two states that are possible evolutions from some initial state under the dynamics generated by the total Hamiltonian at some fixed infinitesimal interval delta t. So the idea here is that we think our theory is a complete one and that it ought to be deterministic, and yet we still have some arbitrariness in our dynamics. And so any two states that are reached under different choices of these arbitrary factors should be thought of as physically equivalent and so related by a gauge transformation. And indeed, by considering two different choices of these arbitrary factors, Dirac shows that each primary first-class constraint generates a gauge transformation. So in other words, the gauge transformation of a function f is given by the Poisson bracket of that function with some arbitrary combination of the primary first-class constraints. But now what about the secondary first-class constraints? Well, with some further arguments that are more hand-wavy, Dirac ends up conjecturing that in addition to the primary first-class constraints, it's also the case that each secondary first-class constraint generates a gauge transformation. Okay, so now we're in a situation where our dynamics is given by the total Hamiltonian, which includes the arbitrariness associated with the primary first-class constraints. But we also have some arbitrariness that's associated with the secondary first-class constraints. So it seems that we have a kind of asymmetry here. So what should we do about this? Well, here I quote Dirac verbatim. He says, "We were led to the idea that there are certain changes in the P's and Q's that do not correspond to a change of state, and which have as generators first-class secondary constraints." That suggests that one should generalize the equations of motion in order to allow as variations of a dynamical variable g, with the time not only any variation given by the equations of motion with the total Hamiltonian, but also any variation which does not correspond to a change of state. So we should consider a more general equation of motion with now an extended Hamiltonian consisting of the previous total Hamiltonian plus all those generators that do not change the state with arbitrary coefficients. And these are precisely the secondary first-class constraints. So the final picture is that the equations of motion are given by the dynamics with an extended Hamiltonian, where this is just first-class Hamiltonian plus an arbitrary combination of all of the first-class constraints. And the gauge transformations are generated by each first-class constraint and arbitrary combinations. Okay, so now we're going to turn to some responses to Dirac. So the first one is by Brian Pitts. He says that one can show by example that each first-class constraint does not generate a gauge transformation. It leads rather to what he calls a bad physical change. And the example he gives is just that example of electromagnetism that we looked at earlier. He says that electromagnetism fails to have the Dirac gauge transformations because the transformation generated by a first-class constraint on its own fails to preserve solutions. So we can see his argument as follows. What we do is we consider the transformation generated by some arbitrary combination of both of the constraints, here where the arbitrary factors are denoted by alpha here and beta. And what we find is that when we transform vector field A, we just get an additional of a term that is the gradient of the arbitrary factor associated with the secondary first-class constraint. And when we transform the potential V in this way, we find it just has this addition of alpha, which is the arbitrary factor associated with the primary first-class constraint. And now, when we consider the transformed equation of motion, which here I just write for the vector field A, since this is going to be the crucial one here, we find that if we assume that the untransformed vector field A satisfies the equations of motion, then we have some restriction on the relationship between alpha and beta that must hold in order for this transformed equation of motion to be satisfied. And what does this mean? Well, if we consider the case where we consider the transformation where we only have a transformation generated by one of the first-class constraints, so this means when one of alpha or beta is equal to 0 and the other one is not, then one finds that this restriction doesn't hold, and so this transformed equation of motion is not satisfied. And so this means that the transformation generated by only one of the first-class constraints is not a gauge transformation. And so on the basis of this, Pitts concludes that rather it's a specific combination of the first-class constraints that generates a gauge transformation. And therefore, that one need not introduce the extended Hamiltonian to account for all of the gauge freedom, since the extended Hamiltonian is motivated by the fact that the gauge freedom is given by the secondary first-class constraints in addition to the primary first-class constraints, which isn't right. Rather, there are only as many independent arbitrary functions of time as there are primary first-class constraints. Okay, now we're going to turn to a second response to Dirac, given by Joseph Pons, who argues that Dirac's proof is incomplete because it only gives an account of gauge transformations as transformations on states that is distinct from what should be regarded as the standard notion of a gauge transformation as a map between solutions to the equations of motion. So unlike Pitts, who's giving a specific counterexample to Dirac, Pons is really pinpointing where in Dirac's argument he goes wrong. And to do this, what he does is he gives an extended definition of a gauge transformation as something that relates two states that are possible evolutions from some initial state, again under the dynamics generated by the total Hamiltonian, but now we consider any time t and not just some infinitesimal fixed time t, delta t. So under this more general account, Pons shows that the form of the gauge transformations is rather given by some combination of the first class constraints with a single arbitrary function of time here given by psi that are related to each other by being the time derivative of the original one. So what this means is that the arbitrary functions of time multiplying the first class constraints are really related to each other. And importantly, what this means is that at a particular time, it reduces to the Dirac gauge transformations precisely because the time derivative of psi will just become independent at a particular time. And so we have these independent generators at a particular time. But similarly to Pitts, what Pons concludes is that it's really a specific combination of first-class constraints that generates a gauge transformation, with the provision that it's specifically on solutions or on histories, but similarly concludes that one need not introduce the extended Hamiltonian to account for all of the gauge freedom. Again, because it's the total Hamiltonian that contains all of the information about the gauge freedom of solutions. Okay, so what is the upshot of all this? Well, we've seen that there are really two notions of a gauge transformation going on. There's the direct view that a gauge transformation is a map from one state to another physically equivalent state. And there's this alternative view that a gauge transformation is a map from solutions to the equation of motion to other physically equivalent solutions. But so far, the debate suggests that as long as we keep these two things apart, both views can in fact be right at once. We just have different notions of the gauge transformation on states and those on solutions. But if this is the case, then what's really the issue? Well, I don't think that we can be satisfied with the way that I just presented the situation. First, because I think there is a conceptual issue with the distinction, because what it means is that individual states along two curves can be gauge equivalent without it being the case that if one curve is a solution, then the other one also is, because the gauge transformations on solutions is more restrictive than those on states. But if gauge equivalence just means physical equivalence, then how can this be so? It would mean that all the individual states along two curves are physically equivalent, even though the sequence of states that makes up one curve is not physically equivalent to the sequence of states that makes up the other curve. And second, I think the debate rests on some questionable reasoning, which is that it assumes that we have to reason as follows. We first determine the gauge transformations using this total Hamiltonian, and then we use these gauge transformations to say whether we should extend the Hamiltonian. But could we reason the other way round? That is, could we motivate the extended Hamiltonian first and then use it to determine the gauge transformations? Now, there are already some suggestions in the literature that this is the right way to go. So returning to this case of electromagnetism again, there's a recent paper by Oliver Pooley and David Wallace who argue that in this case and against Pitts, if one starts with the extended Hamiltonian, then one finds the gauge transformations just are the Dirac ones. And one can see this as follows. So if we now consider extended Hamiltonian, which just differs from the total Hamiltonian by adding some arbitrary factor multiplying the secondary first-class constraint, then this changes the equations of motion just by having now some additional arbitrary function in it. And now when we consider transforming the vector field A and the potential V by an arbitrary combination of the first-class constraints, we find that in particular, the transformed vector field A satisfies the equations of motion when the untransformed vector field A does for now any choice of alpha and beta, because we can just combine all these arbitrary factors together and they will have exactly the same form as the original equation of motion. But notice that this relies on the fact that we now have this additional arbitrary factor in our equations of motion coming from the secondary first-class constraints in our Hamiltonian. And what does this mean? Well, Pooley and Wallace argue that the extended Hamiltonian formalism is really empirically equivalent to the Lagrangian one, in the sense that it reproduces the same equations with just the same role being played by different quantities. And on this basis, they argue that the extended Hamiltonian formalism should be seen as equally adequate for representing the same phenomena. And although I think this is a step towards responding to this alternative view, I think it still leaves open for these advocates of this alternative view to respond that it's the extended Hamiltonian formalism, even if it's empirically equivalent to the Lagrangian one, is still not the right way of thinking about Hamiltonian theories with constraints. So could we do more and argue that the extended Hamiltonian formalism is not just empirically equivalent, but is really naturally required to express all of the freedom present in the theory? And I'm going to argue that the answer to this question is yes, and that we can see this using the geometrical picture of the constrained Hamiltonian formalism. So with that in mind, let's turn to this geometric picture. So the way I'm going to present this geometric formulation is, I think, standard, and I've included a few references at the end of this talk if you want to see more where this formalism appears in the literature. So in this geometric picture, first what we do is we define our state space as the cotangent bundle of configuration space. And it just consists of the points that consist of the pair, the position variable, and the canonical momenta variable. And importantly, defining the phase space in this way means that it comes equipped with a one form given by just the momenta variable times the differential of the position variables, which comes with a corresponding two form omega, which is just the exterior derivative of this one form, which has the property of being symplectic, which means that it is both closed and it is non-degenerate. And importantly, having this symplectic structure on phase space means that we also have some Poisson bracket structure on this space. In particular, we can define the Poisson bracket between a function f and a function g as just the two form acting on the differential of f and the differential of g. And this Poisson bracket will have all the properties that we usually attribute to Poisson brackets, and locally can be defined in terms of the coordinates. So alternatively, one might understand how the two form acts in terms of how we understand Poisson brackets to act. Another fact that's important here is that given a function f, one can uniquely define a smooth tangent vector field through the fact that the two form acting on this tangent vector field is just equal to the differential of f, where the dot here just represents any vector field tangent to the phase space. So what this means is that the integral curves of these smooth tangent fields give the flows of a function. And it's unique precisely because this two form is non-degenerate. And with these two facts, we find that the equations of motion naturally arise in this formalism, since we have that the Poisson bracket of a function f and the Hamiltonian is just the two form acting on the vector fields associated with F and the Hamiltonian, which is just equal to the differential of F on the vector field associated with the Hamiltonian, which we can think of as just the change of F along the flow defined by the Hamiltonian vector field, which is just the derivative of F with respect to time, where time parameterizes the flow of this vector field. So now let's consider the case where we have some constraints. In particular, I'm only going to consider the case where we have first-class constraints, since these are the ones that are important for us, but we can naturally also define the case where we also have second-class constraints. So importantly, these first-class constraints, what they do is they give rise to a submanifold of phase space, which we call the constraint surface, and here represented by sigma. And if the dimension of phase space is n and there are m first-class constraints, then this submanifold is n minus m dimensional. And this surface is precisely the surface where the constraints hold. Moreover, we can define a two form on this constraint surface as just the pullback of the two form on the phase space to the surface. And we find that this induced two form on this constraint surface is in fact degenerate, and so it doesn't satisfy the properties for being symplectic. Instead, we actually call it pre-symplectic because it possesses m null vectors, and these null vectors are precisely associated with the first-class constraints. So what it means to be a null vector here is just that this induced two form acting on the vector field is equal to 0. And we can see that this is the case for the vector fields associated with the first-class constraints, precisely because the two form acting on this is just equal to the differential of these constraints on the constraint surface, and this is equal to 0. And so these form, in fact, all of our independent null vectors on our constraint surface. And we say that the integral curves of the null vector fields, the gauge orbits. So just to see this picture visually, here what I've drawn is I have a three-dimensional space representing phase space, and we have a single constraint that defines a two-dimensional surface in this three-dimensional space. That is the constraint surface. It's precisely when this constraint holds. And here in orange, I draw the integral curves of the null vector field associated with this first-class constraint, which are precisely the points that are connected by the integral curves of this null vector field. But remember, what it means to be a null vector field is that precisely it's a vector field tangent to this constraint surface such that the induced two form acting on it is equal to 0. Now we can see here that this terminology of associating the null vectors with the gauge orbits already suggests that we are taking the first-class constraints to generate gauge transformations. And indeed, that this is being supposed is recognized in the literature on the geometric formalism. So here I give a quote from a standard textbook by Henault and Teitelboim on the constrained Hamiltonian formalism. They say that the identification of the gauge orbits with the null surfaces of the induced two form relies strongly on the postulate made throughout the book that all first-class constraints generate gauge transformations. So in other words, the gauge orbits are just taken to coincide with Dirac's notion of a gauge transformation. So does this mean that this geometric view is subject to these criticisms, particularly the ones we looked at by Pons and Pitts? Well, I'm going to argue that, in fact, the answer to this is no. The geometric picture can, in fact, be used to show that the reasoning in the debate is wrong. So just to go back to what that reasoning was, the idea was that we determine the gauge transformations using the total Hamiltonian, and then we use these gauge transformations to say whether we should extend the Hamiltonian. But geometrically, I think we can reason in a slightly different way. What we can do is we can motivate the extended Hamiltonian independently from considering anything about the gauge transformations on solutions. And moreover, we can determine the gauge transformations on states independently from thinking about the gauge transformations on solutions. And we can use these two facts in order to say what the gauge transformations on solutions ought to be. So just to see how this goes, first we're going to start with this motivation for the extended Hamiltonian. So let's consider transforming the vector field associated with the Hamiltonian such that now we add an arbitrary combination of the vector fields associated with all of the first-class constraints. But now we can use the fact that the induced two-form acting on the vector fields associated with the first-class constraints, because these are the null vectors, is just equal to 0. To show that the induced two-form acting on this transformed vector field is just equal to the induced two-form acting on the vector field associated with the Hamiltonian, which is just equal to the differential of H on the constraint surface. So what does this mean? Well, what this means is that if we're just considering being on the constraint surface, we see that the evolution generated by the vector field associated with H and the vector field associated with H plus some arbitrary combination of the vector field associated with the first-class constraints is not distinguished. Because the induced two-form is precisely the structure one uses to define evolution within the constraint surface. And notice that there's no assumption here made about whether the constraints are primary or secondary. Because each first-class constraint constitutes a null direction on the constraint surface, this is all that we need to say which transformations of the Hamiltonian are dynamically equivalent. So what does this mean? Well, it means that at least on the constraint surface, one can motivate this wider class of equivalence class of Hamiltonians given by the extended Hamiltonian without considering anything about the gauge transformations. It's purely a fact about the structure of the constraint surface. So let's turn to the sense in which states are equivalent. So importantly, on the constraint surface, this induced two-form is such that it only acts on vector fields that are tangent to the constraint surface. But these are precisely the vector fields that are constant along the gauge orbits. And so for functions that are such that they vary along the gauge orbits, the induced two-form is such that it cannot effectively see this change. And so one cannot distinguish the value of a function at different points along a gauge orbit using the structure of the constraint surface. And this provides a sense in which these points are equivalent, namely there is no way to tell using the structure of the constraint surface which point one should evaluate a function at. And so on this basis, we can say that each first-class constraint generates a gauge transformation on states. What this implies is that the gauge transformations on states arises naturally from the structure of the constraint surface without any reference to the dynamics. And notice that this is different from the way in particular that Pons understands the gauge transformations on states as being a particular case of the gauge transformations on solutions. And finally, with these two things in hand, we can think about the equivalence of solutions. So we've already shown that transforming the Hamiltonian to this wider equivalence class of vector fields generates a curve that differs only with regard to where on the gauge orbit it lies at each point in time. And moreover, we've argued that each point along a gauge orbit forms an equivalence class of states. And so naturally from these two facts, we have that each first-class constraint also generates a gauge transformation from a solution to another solution, in the sense that transforming a solution by an arbitrary amount along the gauge orbit at each point will give a new curve that's a solution generated by a Hamiltonian with just a different combination of null vectors. And we have a natural reason to think that these are physically equivalent, since the Hamiltonians of this kind form an equivalence class and the states along a gauge orbit form an equivalence class. So what this means is that the gauge transformations on solutions also arises naturally from the equivalence class of Hamiltonians and of states. So we seem to have that Dirac's definition of a gauge transformation is in fact correct, both for states and for solutions. So where did these responses go wrong? Well, if we restrict the equivalence class of Hamiltonians to just those that include an arbitrary combination of primary first-class constraints, then this will impose restrictions on which transformations can count as gauge transformations on solutions. But as I've argued, this is unnatural in this geometrical picture for two main reasons. Firstly, it distinguishes different null vectors that are structurally equivalent, namely the primary and the secondary ones. And second, it would be to say that the dynamics can distinguish states along a gauge orbit, even though the structure of the constraint surface is such that it cannot distinguish these states. In particular, in the geometric view, we have this independent grasp on the gauge transformations on states. And this is in tension with taking the gauge transformations on solutions to be more restrictive than those on states. So before I conclude, I'm just going to consider a possible response that one might make to my argument. So one might say, well, I've shown that using the extended Hamiltonian reproduces this Dirac view, but the whole point was that the extended Hamiltonian doesn't give us the right answer. Only the total Hamiltonian gives us the correct Lagrangian equivalent gauge transformations. So what I've merely done is show why the extended Hamiltonian is not correct. But as I've argued, to say this would really be to deny that the geometry of the constraint surface captures the full picture of the physical situation. In particular, it requires one to deny that the primary and secondary constraints are on the same footing, even though they seem to be structurally the same in this formalism. So I'm going to present two options I think one might go in order to try and argue this. The first option is to argue that really the interpretation of the primary and secondary constraints is distinct within the constrained Hamiltonian formalism, because the secondary constraints arise from these consistency conditions on the primary constraints. And so one might argue they just play a distinct role in this theory. But I think this response fails for two main reasons. Firstly, once one's in possession of all of the constraints, then it seems that the distinction between primary and secondary doesn't play any role at all. What matters is the distinction between the first class ones and the second class ones. And second, one might see this as just being an accident of the way that we set up the constrained Hamiltonian formalism. If instead one imagined that we, instead of starting with just the primary ones, we imagined that we just started with some set of all the constraints and our Hamiltonian, then it would seem that there isn't any distinction built into our formalism. So this leads on to what I think the second option for arguing against me is, which is to argue that really it's the Lagrangian formalism that provides the distinction. Because in motivating the constrained Hamiltonian formalism, what one does is one starts with the Lagrangian, and then it's only the primary constraints that are imposed when we move from this Lagrangian to the Hamiltonian picture. And so one might say it's really the Lagrangian formalism that provides the basis for this distinction between the primary and secondary constraints. This relies on arguing that it's really the Lagrangian formalism that is the fundamental one, and that the constrained Hamiltonian formalism is somehow derivative on it. But it seems that one could equally well imagine that we started with the Hamiltonian theory and used it to define the Lagrangian one. And second, I think to argue this, really more needs to be said about what the interpretation of the primary and secondary constraints is within the Lagrangian formalism. And kind of as an open question, something that I want to think more about is whether this distinction is really also an accident of the way the Lagrangian formalism is set up. Could we, for example, write the Lagrangian in an equally good way where 4 was the secondary constraints now arises as the primary constraints? So just to conclude, what I've tried to argue is that reasoning from the gauge transformations to the form of the Hamiltonian really gets things the wrong way round. The equivalence class of Hamiltonians can be determined independently from considering the gauge transformations, and this class of Hamiltonians is necessary to describe the freedom in the dynamics. So Dirac was right about the gauge transformations and the role of his extended Hamiltonian, but his reasoning was flawed. So finally, just to go back to some of the points I made earlier about why this question is interesting. Firstly, this question about the relationship to the Lagrangian picture. So what I've shown is that the gauge transformations in the constrained Hamiltonian formalism don't match the Lagrangian ones, at least in the way argued for by Pitts and by Pons. So should we conclude that these pictures are not equivalent? Well, I don't think so, but I think what it shows is that what we need to do is be more careful about how we really translate between these two pictures. And I think this paper by Pooley and Wallace provide a good account of how one does this in the case of electromagnetism. And second, this problem of time, well, what I've shown is that one cannot avoid the problem of time purely on the basis that the definition of a gauge transformation that it relies on is incorrect. So should we conclude that the problem of time does arise within the constrained Hamiltonian formalism? Well, I think the situation is a little bit more complicated in this case because the distinction between the gauge transformations on states and those on solutions is more complicated when the Hamiltonian is itself a first-class constraint. The reason being that the equivalence class of states is then tied up with the dynamics in the sense that the states along the gauge orbits also correspond to the solutions to the equations of motion. So although I think we provided clarity on the conceptual difference between these gauge transformations on states and on solutions, I think more work needs to be done in understanding the case of a Hamiltonian first-class constraint. Okay, that's everything. Thank you very much for listening.
All right. So again, thanks, Clara. It was an amazing talk. It was very, very interesting. It was very clear. All right. So we have a whole bunch of questions already. Let me start with Oliver. I know Brian has a question, and because Brian was mentioned at many points in this talk, we'll definitely make sure we get to you, Brian, also. So just hang on. But Oliver, you go first.
Thanks very much. Thank you, Clara. That was a lovely talk, and I'm sorry I missed the very beginning. So I have two questions. So can I go back to the end of the queue with one of them? So maybe the one to ask first is, I think I agree with almost everything you say. And one thing I've thought is that there's something sort of potentially inconsistent with the kind of thing you might take Pons or Brian to be saying, or well, maybe Pons, in that you're using the kind of Dirac argument. So Pons endorses the Dirac argument as an argument to tell you which states are gauge equivalent, but then wants to seemingly say that only solutions related by the Lagrangian gauge transformations or transformations on phase space that are equivalent to the Lagrangian gauge transformations on solutions are really gauge transformations. And there would seem to be an inconsistency in that, because there are sequences of gauge equivalent states that are included when you go to the extended Hamiltonian, but you're not saying that those are allowed solutions. Now, from the Hamiltonian framework, that just looks like a mess, right? You're saying that these points really are gauge equivalent, but somehow I'm distinguishing between some sets of gauge equivalent points and point by point gauge equivalent points, which I'm saying aren't solutions. So that looks bad. But when you're thinking in terms of the Lagrangian formalism, that distinction between solutions doesn't look bad. It's only when you're kind of operating in phase space that distinction looks somehow incoherent. So I didn't know whether you had thoughts about that.
Yeah, that's a good point. Can you maybe say a bit more about why it's not a problem in the Lagrangian?
Well, so in the case of electromagnetism, when you're working on that Hamiltonian phase space, you've got the this quantity, that the momentum that you can identify as the electric field. But there's a sense in which you don't have that. There's a sense in which Brian's insistence that it's this particular velocity involving A, that's the electric field, is, in the context of a Lagrangian setup, that might not look bad, given that you don't have the momenta there at the base level.
Okay, yeah. Okay, I haven't thought about that too much, but I guess what I would say is that like why should we expect the same thing in the Lagrange, like the way it looks in the Lagrangian one to be the same as the way it looks in the Hamiltonian framework? In this Hamiltonian framework, it clearly is unnatural to have this distinction in the way that you so very nicely described about the gauge equivalence of states. And really, that's the kind of thing that I am trying to argue against. So as you say, with the Pons reasoning, it seems unnatural in as much as what he's trying to do is provide the correct Hamiltonian framework to take both this gauge equivalence of states from Dirac, but think that there's this other one on solutions. I think if we just start with the Hamiltonian framework, that's clearly unnatural. And I think, okay, there's clearly an interesting question here about why there's this difference and what, like, where that difference lies in. But I don't think that would matter to this point about the situation in the Hamiltonian framework. But maybe you think that I should care more about that in my argument.
No, no. It's a quick answer.
Thanks.
All right. So Enrique suggested that Brian go next. So Brian, you're next.
Thanks, Enrique. Lovely talk, Clara. Very nicely presented. So some of you will be aware that, so it's nice to get all this attention, even if it's often critical lately from various people. Some of you will know that I admit to an error in section 9 of my 2014 paper. I think the error is confined to that, however, and much of the rest of the paper will say that the idea that a first-class constraint generates a gauge transformation is either false or trivial. It's not simply a claim of falsehood. And I think the triviality is quite important because one of the things that one tends to see in the extended Hamiltonian formalism, at least in particular cases such as electromagnetism, is it's basically just a de-optimization. I think that's both part of the brilliance of the Cooley-Wallace arguments and part of why I think it doesn't go as far as one might need. In particular, you can equally well de-optimize massive electromagnetism by splitting the scalar potential up into a sum of two functions, and then you can get a gauge transformation by the Cooley-Wallace standards with the second class primary constraint, which I think which would be, I think, a heresy by anyone's standards. I don't think anyone thinks that a second class constraint can generate a gauge transformation. So I think that this is obviously not in your idiom. I tend to prefer reflective equilibrium with examples I understand and see geometry more as a tail than as a dog, at least in my own hands. But I think I would respond that you are mixing trivial activities like splitting one quantity into a sum of two others with physically interesting quantities that are the examples that motivated us to find apparent indeterminism and need constrained Hamiltonian dynamics in general. So I think there's a risk that you're mixing really boring tricks that you could do to any quantity in any theory, or certainly to any constrained theory, even if it's like primary second classes, or many, okay, a little bit, I take that back a little bit. At least paradigm non-gauge theories like Procas massive electromagnetism, you may be stuck, at least insofar as you agree with Cooley and Wallace anyway, you may be stuck mixing trivialities with physically interesting notions. And so I'm wary of definitions of gauge freedom and observables and so on, because we frequently independently understand those things and then try to redefine them again. At least Peter Bergman did. So that's some of my concern, at least.
Okay, so maybe just to say something about this. So I'm not sure particularly what you refer to as this de-Occamization. If it's just the adding additional terms to your Hamiltonian, then I definitely haven't argued that one can do that for the second class constraints. And like geometrically, the second class ones have a very different like understanding, right? They're not these null vectors of the constraint surface because they are not tangent to the constraint surface. So at least like the distinction between the first class and the second class ones clearly arises geometrically. And I don't think a consequence of what I've said is that one could just arbitrarily add the second class ones as well to one's Hamiltonian. But maybe you meant something else by that.
I didn't say to add the constraints. I said to de-Occamize. So whatever you have to do to split the scalar potential into the sum of two quantities, which turns out not to be strictly adding. You have some other, you have to fudge a little bit. So the generalization is de-Occamization. It's not adding constraints to the Hamiltonian. But if you think de-Occamization is a really boring trick, like I say, Clark Gleamore, this is just force equals Gorse plus Gorse plus Morse, who cares? If you think that's a boring trick, then, as I do, then that's a trick that you can play in paradigm non-gauge theories as well. So you might have trouble. I mean, maybe you could say you're not interested in de-Occamization, you're interested in this geometry, and therefore it's just an accident that it overlaps with triviality, and your view isn't generically trivial. That might be an interesting, maybe that's what you would say.
Yeah, I think that is probably what I would want to say. I haven't worked through that example you'd give, so I'd like to see it in more detail. But I don't think that what I'm trying to motivate is, as you say, this triviality or on the basis of some kind of de-Occamization reasoning. Rather, it's about what's motivated, like what is the natural interpretation of this geometric formalism, and particularly what naturally should be regarded as these equivalence class of Hamiltonians. And that's the thing that's motivating this.
Thank you.
All right, thanks. Next, we have Enrique.
Thanks, Clara. That was really nice. I was just wondering if it's more, well, it's a question and a comment. Wondering if you know about this covariant symplectic formalism, because to relate the Lagrangian formalism to the Hamiltonian formalism, it is most suited. In fact, there is one point that is relevant to your talk about the problem of time, that it is well known that the Hamiltonian constraint that generates, well, the Hamiltonian constraint of GR, the super Hamiltonian constraint is sometimes called, would only generate refoliations in the Lagrangian formalism for spacetimes that satisfy the Einstein equations of motion. And I was wondering if you can see that fact just from your form without using this more, this more recent technology. I wouldn't say it's more advanced, but it's more recent technology. Can you just, can you extract that fact from this formalism that the Hamiltonian, because for me, that is still a bit mysterious. It's not something that I fully understand conceptually. How come the Hamiltonian constraint is equivalent to refoliations only for spacetimes that satisfy the Einstein equations, and not just for general spacetimes, because the first class constraint shouldn't distinguish between that. So yeah, that's.
Yeah, this is something I'm also puzzled about. So, and particularly that case is one that I want to think more about, but wanted to think first about this non-relativistic case and really understand what's going on there before moving to that relativistic case. So just to say, I agree with you that I don't really know, because there's clearly something conceptually interesting going on in that case, and something that I want to think more about.
Thanks.
Thank you,
Thanks. Yeah, I'll go to the back of the queue.
Enrique.
Other things to say, but.
Okay.
So I have, as usual, I have a whole bunch of questions. I like to give other people priority before I start asking questions. Good, Gabriele. If we do run out of questions, I have plenty to ask. Gabriele, go ahead.
I thought I would go after you, but
No, please go ahead. I want to prioritize everybody else. Please go ahead.
okay. So what you present is sort of it's a very different way from what I used to think of gauge transformation. So I'll just say how I think about it, and then you can tell me like points of connection or disconnection and so on. So the way that I understand symplectic geometry is that the conjugate momentum is not uniquely defined. There are infinitely many conjugate momentum that you can pick when you have a set of Qs, and so there is an arbitrariness on the representation in Hamiltonian mechanics. So if you ask for the canonical transformation that keep Q and Q dot the same, you get the space of the gauge transformations. And the idea to me, the way that I understand this is that the conjugate momentum is not something that we measure directly. What we measure is kinetic momentum, velocity, mass. So those are the things that we measure. So as long as our state representation and equation are invariant, the Q and Q dot remain the same, we can do everything we want to the P's. And so to me, the gauge transformation is really a choice of equivalent representation in respect. You could use second order equations, but prefer first order. It's nice for doing statistical mechanics, and therefore we stick in these P's that are sort of labels, not so physically significant, and then we have a map between the P and the Q dot, which are the things that we care about. And interestingly enough, something similar happens in quantum mechanics, because again, the physics in quantum mechanics is in the projective space, but we like the Hilbert space because it's linear, it's nicer, and so on. And there are infinitely many Hilbert spaces that point to the same projective space, because you're removing information when you go to the projective space. And if you look closely, the arbitrariness is really a choice of phase for each position. So it's really a gauge transformation, and therefore, again, it's really a choice of representation. So that's sort of how I think about gauge transformation, is that the gauge arbitrariness is basically a choice of representation that is non-physical, and we pick it. So I don't understand how it relates to constraint, unless the constraint is that I keep the Q and Q dot the same, I guess. Do you make any sense?
Right, so, yeah, I think so. So at least I think the way you're understanding the gauge transformations is precisely the Lagrangian ones as being taking place in this space where you think of just having the positions and the velocities, and you're thinking about what transformations preserve the action or the thing in that space that defines your dynamics. But the constraints arise precisely because when you're moving to the Hamiltonian framework, as you say, you can't uniquely define these momentum, but it's precisely the constraints that allow you to then do this one-to-one mapping from the Lagrangian case to the PE, between the position velocity space to this position momentum space. And it's precisely the constraints that allow you to do this move back and forth now. And so like, what you're saying is you understood the gauge transformations, I think, is just the Lagrangian one. So the question is, why should we care about these ones in the Hamiltonian one? Well, precisely what's going on here is it seems like in as much as the Hamiltonian framework is an equally good way of describing the same kind of systems, we're asking, like, in this framework, what are the symmetries of this formalism? And then we have this question of, do they match the ones in this way that you're thinking about? And like, how do we translate between them? And like, how should we understand the two? So I think, as you're saying, like, you might want to just say the Lagrangian one is the primary one, and this is how we should understand the gauge transformations. And I think that's how some of these people of the alternative view are going, is they're saying, yes, we should, like, the Lagrangian ones are our primary ones, and they should be the ones that tell us what the right one is. But I don't know if it's clear why that should be the case. Like, you talk about how you measure the velocities and stuff, but there's equally well an interpretation of the Hamiltonian one that doesn't require one to, I think, start with some prior understanding of the Lagrangian one. It is its own formulation that has its own distinct interpretation. And so precisely the point is that these constraints are allowing us to make this move, and now we want to understand, under this formalism with constraints, what are the symmetries of this formalism? So yeah, I don't know if that answers your question, but
I guess, what does the constraint represent? Like, is it one constraint per choice of conjugate momentum, or it's a constraint that is valid between all choices of momentum?
I think the sorry, I'm just having to think. So maybe the way to think about it is that we're particularly thinking in the case where one's like the Hessian of the Lagrangian is not invertible. And one way to make it invertible is precisely to impose these constraints. So you're only considering like a subset of the points where these constraints hold. And on this space, then we can define this mapping uniquely. And so the sense is that these constraints are like imposing what counts as like an allowed state in the Hamiltonian formalism. Maybe someone else can describe this better than me.
Can I just give a suggestion, just to I think, for me at least, what made it clear, Gabriele, the relation, at least heuristically, is that the second other theorem establishes some linear relationships between the Euler-Lagrange equations. So the Euler-Lagrange equations are not all independent. That means that they won't be able to propagate all the degrees of freedom uniquely from an initial surface to a final surface, because they're not independent. So you can only propagate some constraint, some subset, and the constraint tells you what kind of subset that can be uniquely propagated.
Okay, so it tells you how to decouple in independent degrees of freedom. Okay, that makes sense.
Thanks, Enrique.
Okay, so I have a question. So Eric Curiel has had an argument for many years that he's made in a couple of different places, that the Lagrangian and Hamiltonian formulations really are not truly isomorphic, and that there is a distinct sense. Again, I'm not necessarily endorsing this view. I'm also not endorsing this view. I'm not taking a stand on this issue, but there's a sense, he argues, in which the Lagrangian formulation is truer to the fundamental structure of classical physics. And he, you know, the argument he makes is that there's in the Lagrangian formulation, there is arguably a definite meaning of interactions. There's a definite way to talk about a non-interacting system compared with an interacting system. And so the Lagrangian formulation gives you a way to talk about interactions in a definite way. When you switch over to the Hamiltonian formulation, it's not that the Hamiltonian formulation, Lagrange formulation make distinct empirical predictions necessarily. It's more that the Hamiltonian formulation contains less structure. And so it doesn't give you a way, no pun intended, but it doesn't give you a canonical way to identify, to distinguish between non-interacting and interacting theories. It seems to have less structure in it. And in a sense, this isn't totally shocking. You know, the class of changes of variables that are available in a Hamiltonian picture is just much wider, at least prima facie, than the class of changes of variables in the Lagrangian picture. In the Hamiltonian picture, you have the freedom to do canonical transformations that completely mix up what you mean by Q's and P's. And in some ways, that's fantastic. If you want to discover the Hamilton-Jacobi formulation, you really like that you can do completely, you know, out there changes to canonical transformations. But there is a cost. The cost is that freedom, in a distinct sense from maybe gauge freedom, but that freedom also means you've got less structure, and maybe there isn't a complete perfect equivalence between the Hamiltonian and Lagrangian pictures. So you may not have an answer to this question, but I'd be curious to get your thoughts, or really anyone else here. Is there a potential connection between maybe the different way we think about primary and secondary constraints in the two pictures, the Lagrange and Hamiltonian pictures, and the fact that is it possible this is touching upon some of these conceptual distinctions between the two pictures? That makes sense?
Yeah, it makes sense. And I think that debate is super interesting in its own right. And I also know that just as Eric has argued that the Hamiltonian one has less structure, there have also been arguments that the opposite is true, and that the Lagrangian one has less structure. And there have been arguments, like Thomas Barrett has work on this, that in fact, this depends upon, like, this debate is about how much structure they're really imbuing into these formalisms, and that there is also a way perhaps to think that they are just equivalent. So a lot of this depends on what structure you're taking both of these frameworks to have. And so just to say, I think obviously what this suggests is that the picture is more complicated than just the one that maybe is suggested by the Eric Kuehl picture. And maybe we need to think about both of these sides when we're answering this question. But I do agree that thinking about, at least I don't think the Eric Kuehl paper talks about constraints at all. And so thinking about how the arguments in that literature go when we're considering the case of constraints, I think is also an interesting one. So yeah, just to say, I think there is lots of interesting things to be thinking about there.
Jacob, if I can add, again, it's not true that you can mix everything you want with the Q's and the P's, because the P's are not physical. You don't measure them. Like quoting a colleague of mine, all my measurements are gauge invariant. So
maybe your measurements are. I'm just joking. You know, I didn't mean to say that from a physical I mean, I'm not making a physical claim here. Yeah. Certainly, if I choose to define, if I've got a particle, it's got position, and I'm using the Q's to represent position, I can certainly do a canonical transformation and mix position and momentum and get something that might not be directly observable. Right. But I think this doesn't get around to Eric's point that, and again, there are a bit counter arguments, but I think this is not one of them. That's precisely the problem. He would argue that the very fact that we can mix things that seem like seeming observables empirically, like positions, with totally other things, and the Hamiltonian formalism doesn't seem to care. The Hamiltonian formalism doesn't seem to be able to tell you, whoops, you've just done something, and now the thing that you're doing is not going to be observable anymore. Is exactly his problem, that it's not as close to physical reality. It's not as close to what classical physics really is. The Hamiltonian formalism, yeah.
But the symplectic space does not. But once you have a Hamiltonian, so now you are in the contact manifold, then you can tell.
Yeah, no, that's
Trajectory, and then you measure the Q dot.
no, that's right. Yeah. Okay, yeah, that's a fair point. I have more questions. Anyone else have questions?
I think
Okay.
Ollie has.
Oliver is raising his hand.
Oh, I'm sorry, I didn't see Oliver. Please go ahead.
Sorry, I was looking for the hand and couldn't find it. So can I ask the question, but just, I mean, in the context of electromagnetism, when you move to the extended Hamiltonian formalism, David and I wanted to say that it's actually is the momentum you measure, because it's the momentum that's the electric field. It's not the A dots. And it's precisely because the A's have this gauge redundancy that there's a sense in which you don't measure the A dots, where you're taking the A field to be the configuration variable. In the Hamiltonian formalism, it's exactly the momentum that gets and end up satisfying the equation that identifies it as the electric field. But my question is just it's going to be an expression of kind of lack of understanding on my part, and I'd be interested to know what you want to say about this. So it's true that it's natural in the geometrical picture to move to the extended Hamiltonian. You've got a nice geometrical statement of that theory. But of course, Brian and others are right that it's not just these particular transformations of the gauge transformations that map solutions to solutions. If you want to have gauge transformations that correspond to the ones you have in the Lagrangian formalism, they are the symmetries, they are the gauge symmetries that map solutions to solutions for the non-extended Hamiltonian formalism, which of course you can, so how are we to think about that from a geometrical perspective? So we've got and how are we to think of different Hamiltonians that are giving us different proper subsets of curves that you get from the full extended Hamiltonian formalism. So I mean, you said that these theories are unnatural from the geometrical point of view, but is there anything more that you can say about how we should think of them working? And so thinking in terms of the intrinsic structure of the full phase space in which the constraint surface lives, and just thinking of the Hamiltonians as just functions on this thing, and using the Poisson brackets to get the to understand the dynamical curves, which will all lie on the constraint surface. But now they're picking out a proper subset of the curves that you think are the natural curves to consider in terms of the intrinsic structure. So you're using more than the structure that you're getting just by restricting to the constraint surface and considering the pre-symplectic form on that. You're having to use the full structure of the non-physical phase space. But is there anything else to say that makes what's going on intuitive?
So I think you've honed on something that is really important here, which is that at least on the constraint surface, these Hamiltonians are in a sense just equivalent. They just form this equivalence class. So choosing just a subset of them doesn't make, it's just picking a smaller equivalence class. And so like there doesn't seem to be any natural sense just looking at the constraint surface to say something that's different about those particular class of curves, since effectively they're just, as I say, just a smaller subset of this already equivalent set. And so it seems weird, why should one just like restrict oneself to that one for any reason? So in order to say something about that, one would have to move off this constraint surface and now think about these points in this full phase space that include these points that we in some sense don't think we should think of as like physically allowed in some sense in this Hamiltonian framework, because there are these points where the constraints don't hold. So how should we think about that? And in particular, like what there's an interesting question here of, is it enough to describe this Hamiltonian framework to just define everything just in terms of the constraint surface and take that to be our theory without including any of these points? Or should we think that there's somehow something interpretational about these points that are somehow like counter to what we would ever find, in the sense that they're not the points that ever satisfy the constraints? So not to say that I think I have an intuition of how this distinction on this full space works, but to say that I think there is something interesting here about the motivation for thinking about this wider class of points compared to the points on the constraint surface. And what I'm just trying to say in this talk is that, like, let's just consider the constraint surface to give us all the structure that we care about. Then it seems that there's nothing natural about restricting to this class that's just these primary first class constraints, because they all seem to just play the same role here. So I don't think that answers your question, but just to say, I think I agree that you're going to have to do something. You're going to have to move to this full space to try and make this distinction between these class of curves.
Okay, I have a question. So this is just like a genuine question about one of the claims in the talk that I didn't understand. So early in the talk, you referenced a point made by Brian about how it was only certain linear combinations of these constraint functions that generated a valid gauge transformation in this electromagnetic example that you were doing. I guess I didn't quite see how that particular critique was resolved in this picture, because in the geometric picture that you provided, at least naively, it looks like any linear combination of the constraint functions is going to generate a null direction along the constraint surface. So I'm not seeing, I guess, how that accommodates Brian's point. So can you help me understand what's going on there? Because it seems to be from the geometric picture that it should be that any linear combination of those constraint functions should generate a gauge transformation. What am I not seeing?
Sorry, so just to ask a question again. So you're asking, so the Brian argument is that we can see that really it's not just any arbitrary combination of first class constraints, it's that there's some restrictions on what that relationship is.
Right.
And in the geometric view, it looks like it's actually just an arbitrary combination of them. Yeah. So how do we, your question is like, how do we get this specific combination out of the
right? Because in the geometric picture, it looks like any linear combination of the constraint functions is going to correspond to an arbitrary linear combination of null vectors, which, because of linearity of the symplectic form, is still a null vector.
Mm-hmm. So as I was kind of saying with Oliver, I think in order to try and get the specific combination view, you're going to have to like impose on your formalism to say we're only going to think of Hamiltonians such that we just add like Hamiltonian vector fields on the constraint surface such that we just add some combination of just the primary first class constraints and don't allow adding the secondary first class ones. And then when we think about the trajectories that are such that they are like evolutions from one of all the different Hamiltonians in this more restrictive class, then supposedly one will find that the only transformations between those curves that map, like between those solutions, will be this more restrictive class, namely this specific combination. So the sense is that what I'm trying to argue is that to try and get that position, one would have to arbitrarily fix just a subset of one's Hamiltonians vector fields, like part of this equivalence class, to define the dynamics, and just say the other ones don't count as allowable trajectories. Does that answer your question?
I think so. So I have more questions. Anyone else want to ask a question? I have a few more. Okay, happy to go to my next question.
I think Ollie actually has.
Oh, please, yeah, Oliver, please go ahead.
So I don't want to jump in ahead of you, but I do have a question for Brian related to his question to Clara earlier.
No, please go ahead.
Okay, well, it's quite, so can you say, Brian, with this massive electromagnetism example that you think is going to cause a problem, is it going to be still true in that picture that arbitrary transformations generated by, transformations generated by an arbitrary combination of first class constraints are going to count as gauge transformations of states? So for any point and for any solution of the Lagrangian equivalent Hamiltonian, and any point on the gauge orbit thought of geometrically, I can find some Lagrangian equivalent solution that passes through that point, which is kind of the Dirac way of thinking about it. And if so, you know, what you want to say about this theory is still facing this sort of apparent incoherence between claiming that these points are gauge equivalent, even though certain curves involving a sequence of gauge equivalent points are not gauge equivalent solutions. And I think your answer to that is that we shouldn't think of the content of the theory as exhausted by functions on phase space.
Yes, thank you. So my point was about the primary constraint only in Proca. So I claim that you and David will be committed to saying the primary second class constraint generates a gauge transformation in exactly the same way that the primary first class constraint does in Maxwell. So I make no such claim about the the secondary constraint. It's only the first class. And I could say more about why that happens if that's interesting. I should maybe have something, some math to show in public reasonably soon. I think that, yeah, you and I have not easily understood each other regarding equivalence over time, but I continue to think that the equivalence between the Hamiltonian and Lagrangian formalism is diachronic, because you have a relation P equals VLD Q dot, or alternatively Q dot equals VHDP. And therefore, I tried to avoid saying anything about equivalent states because Lagrangian states are thicker temporally. And I'm wary of the notion of Hamiltonian states because they don't have the same temporal thickness as Lagrangian states. Being first order involving because they have lower order derivatives. So I try to avoid saying anything about equivalent states and only think about equivalent trajectories. But the crucial point I can clearly say is I was only talking about the primary, not the secondary constraint in Proca.
But wait, in Proca, aren't the constraints all second class?
Yes, that's the reductio from my perspective.
But I don't see how that undermines the geometric picture, since the second class constraints aren't defining a constraint. Maybe I'm missing something here, right? The second class constraints aren't used geometrically to define a constraint surface.
Okay, so my answer is admittedly designed more for Oliver and David, and it maybe only contingently applies to Clara. It's the main thing I have to say at the moment, so that's part of why I'm saying it. Her formalism will be committed to saying, here's a gauge transformation in electromagnetism, where you change the electrostatic potential by replacing V by V plus your favorite function. And for her, that's interesting. My point is, if deochemization is what we're generalizing, then you can deochemize Proca and have the primary second-class constraint generate a gauge transformation, which is contrary to the conventional wisdom, because along with the idea that every first-class constraint, apart from a few weird ones, generates a gauge transformation, the orthodoxy also holds, along with the alternative view, that no second-class constraint generates a gauge transformation. So I take this to be a reductio of the idea that there's anything interesting, at least, about anything that I could construe as simply deochemizing. So deochemization was both how Oliver and David showed that part of my section 9 was wrong, and I claim how the counterexample does not go very deep or really vindicate orthodoxy, because it implies something heretical by any standards, I think, about second-class constraints. So this applies to Clara's view only perhaps for examples that are sufficiently like electromagnetism. So Yang-Mills, GR, could say something, could say, but of course, those are the main reasons we care about gauge theories. So you might say all the important ones, you might say, would have the same point holding.
Maybe I'm not understanding this point about deochemization. I thought that part of in Proca, for instance, because the second class constraint, you can just eliminate that degree of freedom from your phase space, because you can solve, the constraint is invertible, you can solve for that. The time component, whatever the conjugate momentum of A0, you can solve for that explicitly. It's non-local, but you can solve for it, which you can't do in the case where the mass is 0.
That's true.
Right.
That doesn't count against my point, however. So my point is, if you think that you get a gauge transformation by replacing V by V plus mu, where mu is your favorite function, then I'll say, and you generate that by the primary constraint, which is Maxwell's first class. Well, I can do the same trick construed as deochemization, namely replacing V by V plus mu in Proca, which is also generated by the primary constraint. Now, you might worry, it's second class in Proca. Yes, that's true, but second class here is a relation with the secondary constraint, and I'm not using the secondary constraint. The primary considered all by itself has 0 bracket with itself, and hence behaves exactly the same in Proca as it does with Maxwell. So, the primary by itself doesn't know that it is second class. Only with the secondary makes it second class, and that's because I don't use the secondary constraint. The second classness is irrelevant, and that's why I can generate a heresy, I claim, using the same reasoning that Oliver and David correctly used against my section 9.
Right. I think, this is a very naive comment on this. I think the key issue here is basically, do you think that primary versus secondary, this distinction between primary versus secondary is really a meaningful distinction? So when you say in Proca, your primary constraints all alone are first class with themselves, and you're saying, let's just ignore the secondary constraints. And I think Clara would say, no, actually all the constraints are constraints, like all of these primary, secondary, and we should all chide Dirac for creating this horrible nomenclature of primary, secondary, first class, second class. Who thought that was a good idea? Nonetheless, maybe this distinction between primary, secondary constraints just never should have been reified in the way that it was in the original point. And I think that's what is elucidated by the geometric perspective. And then geometrically, Proca is just a system with one fewer degree of freedom. And geometrically, there is no constraint surface. Like, it's just not and this is a naive perspective on this, but that would be my understanding of the difference between these two points of view.
Okay, yeah. So I mean, I guess I trust the Lagrangian formalism. I'm aware that there are, I mean, in certain cases, I don't want to say the. Thank you, Enrique. I'll try to understand that. So I trust the Lagrangian formalism. I don't particularly trust the Hamiltonian formalism unless I can see how it's mathematically anchored in the Hamiltonian formalism, excuse me, in the Lagrangian. I mean, the Hamiltonian formalism does have this interesting freedom, as Jacob mentioned, and it's very useful in celestial mechanics. People do, the old days, and people still do this in some cases. They make canonical transformations to get rid of the interaction terms so that you can get out to fourth or fifth order to figure out the solar system in a way that you would never otherwise figure out how to do. That's great for solving problems. My opinion is it tends to be misleading in terms of conceptual issues. So I think Jacob at least articulated Curiel's view, which I kind of sympathize with. Now, there are cases where so you can, in certain instances, for like say in GR, if the spatial curvature is non-zero, you can treat the lapse function as an auxiliary field along the lines of Bayerlein-Sharp-Wheeler. And Julian Barber likes to talk about that, for example. And then you can make what would have been a secondary constraint show up as a primary. So I don't want to say that the distinction is carved in stone forever, so that there's no reformulation that can change it. But I do think that there's something important that the distinction picks out in our garden variety, naive default formulations, at least, and exactly what that amounts to in a way that's invariant under every trick you could pull with auxiliary fields, I'm not sure. But basically, I think that there's something to the primary versus secondary distinction, and at least to, in a rough and ready way. So I hope that helped. It made some sense, at least. Thank you.
Gabriele's point about statistical mechanics, you have to do that on phase space too. That's also, I think, an important. Hard to do statistical mechanics in a Lagrangian formulation.
Yeah, in particular, if you want to calculate the entropy, it has to be expressed in QNP, otherwise you get like the measure of phase space as how you count the states. So that's important.
I had a question for the group, especially Clara, since you showed the Hanot and Teitelbaum book. Has anyone achieved any insight into this question by using the classical, BRST formulation where you expand the phase space, add these anti-commuting variables, and in a sense, then you sort of get just one gauge transformation, which is this BRST charge, that kind of all of your gauge generators are basically created by this one charge. And I don't know, I find you totally lose any geometric picture then, because they're dealing with these anti-commuting things which have no intuition. But I don't know if anyone's looked at whether that adds any insight into these questions.
I almost did at the beginning of my PhD, and then I was told not to.
Yeah, I don't know enough about that formalism to say anything about it. That part of the book I'm much less clear on. So, but thanks.
All right. Well, we have like 2 minutes left, so I don't know that we have time for anything other than a very short question. I don't know. Brian, did you see Enrique's point in the chat about thinking about things in terms of the covariant symplectic formalism and this distinction you'd made between, thick states in the Lagrangian picture versus well, I don't know what the thin states in the Hamiltonian picture.
Yes, I see. I don't have any particular response at this point, but I appreciate Enrique's pointing that out.
All right. So I think with the remaining minute and a half, I want to thank our speaker again for an amazing talk. This has been an extremely interesting and informative discussion. And thanks to everyone for being here. Your time is very valuable, and we all really appreciate that you're spending your time here with us, talking about these really interesting things. So thanks to everybody, and again, thanks to our speaker. We'll meet again in 2 weeks. As usual, we're on a 2-week schedule. So stay tuned for an announcement with the speaker at our next session 2 weeks from now, November 15th. It's going to be Grace Field, who'll be talking about quantum tunneling times and their interpretation. So stay tuned for an announcement about that. And otherwise, be safe and be well, everybody. It's good to see you all.
Thank you so much, Jacob.